I'm recording. Okay. Hello. It is summer semester 2025, and this is a revision seminar for Maths 1B. Hello, those who are watching this in the future. Of course, we don't really know how much future there is for Maths 1B. We'll see how we go in the new university. Don't even know if there's going to be a summer school next year, so that may be interesting. They might be cutting in part the maths courses and putting them back together a different way. The current suggestion is that there'll be a whole course for algebra that takes the algebra from 1A and 1B and puts it in one course, and a whole course for calculus. Anyway, they're still writing those, so we'll have to wait and see. It'll be too late for you guys. That's fine. It'll be all good. Yeah. So many questions I need answers to do my job, but we don't have any of them. Okay. So there you go. There's a bit of history if you ever watch this in the future once the new university started. Okay, so I've had some requests. I'm going to start with one, which is linear regression via orthogonal projection, which is at a particular page in the notes right at the end of the orthogonal projections bit. And what I'm going to say is that when I read this morning, I've read it before, but when I read this morning, I realized anew that they didn't really use orthogonal projection to do this. They use like one of the features of orthogonal projection, but not the actual act of doing orthogonal projection. So that's why it doesn't feel like it matches with anything around it, because it just doesn't. Okay. So I'm just going to talk this out because I can't remember how to do it off the top of my head, and I will look it up just to make sure I match the notation in the notes. But what they're trying to do by putting this in Maths 1B here is to make sure that they've said something about this so that when a future course brings up that linear regression is orthogonal projection, they can claim they told you. And that will happen if you do any machine learning courses in the future, because that's all based on linear algebra. It's a big claim. They do it all the time. Got to cram a whole lot of crap into Maths 1A and Maths 1B, and then can now claim that you remember it forever, whenever it comes up in all future courses. That's one of the reasons why we allow second years to come to the Maths Learning Centre. At the very least, you can say, I'm sure this was in Maths 1A. Can you help me remember it? Okay, anyway. So just ordinary simple linear regression is designed to take a whole lot of points and try and draw a line of best fit. And the way that it does that is there are many ways to choose a line of best fit, and the way that ordinary linear regression does it is it finds all these vertical distances to the line and, well, this is what it looks like it's doing. So if you have a candidate for your line of best fit, you find all the vertical distances from the points to the line, and you square them and add them up. And then you go, aha, that's the answer I've got. And then you try all different lines, and they'll all give you a different answer for that sum of squares. And what you want to do is choose your line in such a way that that total sum of squares is the lowest it can possibly be. That's how it's done. So the sum of the squared vertical distances to the line is often called Q for reasons I don't understand. And what you want to do is you want to choose your line so that that answer is as low as it can possibly be. So different lines give different answers for Q, and choose a line with Q the lowest. That's how most people describe what linear regression is. And in the notes, they'll say that Q, so given the line like y equals ax plus b, Q, which is a function of which line you picked, so you've got the a and the b, and it's the sum from I equals 1 to however much data there is of the y value from point number I minus a times the x value from point number I plus b squared. So this is this value here, the y value for so this is like this I is traveling between, this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, that's what the I is. And when I is, say, 1, 2, 3, 4, 5, this will be the y, no, let me do 4. This is the y value for point number 4. And then this value here is what ax plus b works out to be for that particular point number 4. And so you have to subtract them to figure out how long that is. And then you square it, and then you add up all those things. That's what this means. And that's what's written in the notes, probably. I should just... I looked it up on one of the devices that I own and can't remember which one I've used. Oh, I know where I did it. Yeah. Yeah, so a subtraction is designed to find the distance between things. We find the distance between this, and then that's what it is. And just to point out that what you have is you have a point x1, y1, and a point x2, y2, and a point x3, y3, and all the way up to xn, yn. So that's the names of all of the points that are here. And this one is that point, and this one is that point, and this one is that point. And when we say yi, we mean you pick which one you're up to. This is like I equals 1 and I equals 2. How are we feeling? Okay. So that is one way of doing this. And you may wonder, why would you square those distances and add them up? So what's he saying? Sorry? I'm going to repeat that. If some of them are below, that'll make them negative, and they'll cancel out the positive ones. And in fact, if you have chosen your line of best fit correctly, they will cancel out, because there should be just as many below as there are above. Otherwise, it wouldn't be in the middle. So that is, but you know, why didn't you just do the absolute value and add them up? Why did you square it? It's a great question. There are good reasons. Squaring is much easier to deal with if you're going to do calculus on it. Absolute value calculus is but also the real reason is that you're not really in 2 dimensions here. You are really in n dimensions. Because what you're imagining here is not that you have n points each with 2 coordinates, but that you have 2 points each with n coordinates. Like that. That is what we're doing. And if you want to know, yep, cool. And so if you're going to do ax times b, so ax plus b, here we go, ready. So if we have ax1 plus b, and ax2 plus b, and ax3 plus b, all the way up to axn plus b, they're all the points on the line of best, they're all the x coordinates for the lines points on, sorry, these are all the y coordinates for the lines points on the line of best fit. And what you would like is for all of these y coordinates to be as close as possible to these y coordinates. That's what you want. Because that would mean that all of this line is as close as possible to all these dots. So that's what you want. So these are the actual y coordinates, and these are the y coordinates on the line of best fit Well, it might not be the line of best fit. It's on my current candidate for the line of best fit. I've just chosen a random A and B. And I would like these to be as close as these, which means I want this point in n-dimensional space to be as close as possible to this point. Other way around, this point in n-dimensional space to be as close as possible to this point in n-dimensional space. And how do you tell whether vectors are close to each other? You find the distance between them, which is made by subtracting all the coordinates and squaring them and adding them up and square rooting. And that is why we're adding up the squares of things, because what we are actually doing is the n-dimensional version of Pythagoras' theorem to find the distance between 2 points. It is super cool. And when Pearson and Fisher, who, I don't know, there's about 3 or 4 mathematicians who were working on this in like the 1890s to the 1920s. When they invented this, it was so clever. And no one understood it, so because it was too clever. And so but in 100 years, we should have figured out how to explain it by now. So here we are. And so we're going to try and find this point, y, not y, but slow down, David. Come back. What I'm going to do is I'm going to write this vector as a lots of x1, x2 up to xn plus a vector that's all b's. Is that okay? And this is the same as a lots of x1, x2, xn plus b lots of 1, 1, 1. Right. You may note that this is a span. We have a vector here, 1, 1, 1, and a vector which has all my x coordinates from my data. And I want to have some multiple of this one plus some multiple of this one. It's the span of 2 vectors. That means that this, if I think about all the possible A's and B's, this is a subspace. And if I want to find the nearest point to this on that subspace, that's what orthogonal projection does. I'm just going to write it as well. So what we have is that we want a x1, xn plus b1, 1, 1 to be as close as possible to y1 up to yn. Damn it, I've switched to a small n, sorry about that. And this here plus b1, 1 with a and b being everything in R is the span of x1 up to xn and 1, 1, 1, which is a subspace. Okay, so if I want the nearest point on this subspace to that point, that's what orthogonal projection does. So point on subspace to y1 to yn equals the orthogonal projection of y1 up to yn onto the subspace. And that's all well and good. And we can go, hey, cool, isn't that fabulous that by switching my perspective from this being a list of points, of n points with 2 coordinates and turning it into a list of 2 points with n coordinates, I can now pitch what I thought was drawing a line of best fit into orthogonal projection onto a subspace. And you go, that's some cool maths philosophy, what fun. But then actually figuring out the answer is a whole other thing. How are we feeling? So what orthogonal projection will do in this case is it will find the nearest one of these to there, and that will tell you what the A and the B are. And once you've got the A and the B, you can come back and go, aha, it's the line y equals ax plus b. That's how you do it. And so, yeah, what that'll do is it tells you A and B. Okay, so here's the thing. Traditionally, the way that you do orthogonal projection is you do the Gram-Schmidt process on the basis. So you can make an orthonormal basis. And then you dot this with the two orthonormal basis vectors, multiplied by the orthonormal basis vectors, add that up, take that away, and then, all of that. Says, you don't take it away. No, you just dot it with that. So you need to do the Gram-Schmidt on these two. All right, and it's really hard to describe how to do the Gram-Schmidt process on a vector that you don't know what it is. This one I can do. Gram-Schmidt process on that is great. The length of this vector is n, root n divided by root n. Awesome. But dotting this with this, actually, that's so cool. It'll totally work. Huh. Anyway, well, what you should be doing is doing this with V1 and this is V2, and you do normalize V1 and V2, normalize V1, do V2 dot V1 times V1, and take that off, and then normalize that, and then you have an orthonormal basis, and then you'll do Y dot the new V1 times V1, and then Y dot the new V2 times V2, and that will be the answer. And that's great, except, sure, that's not what the course notes did, which I find really distressing. Yeah, that's not what the course notes did. What the course notes did is they went, okay, cool, let's just give names to everything. This vector of all the Y coordinates of the actual points is called Y in bold. But I put an underline because I can't write bold on my piece of paper. And this vector, which is X, with all the X coordinates of the original points, is X. And this vector, which is all made of ones, they called capital lambda. Okay, so you're wondering the lowercase lambda is this and the uppercase lambda is this. Yay! It's basically an upside down V. And it makes an L sound in Greek. So why they've called it lambda, I don't know. In some courses, what they call this vector is a bold 1. Just so you know, if you ever see it in the future. And what that means is that they can now say that we want the orthogonal projection of Y onto the span of X and lambda. Technically, it's a bold lambda, so I'll just underline it. So I've just rewritten what I had before, but in symbols. And the way you would do that is you'd Gram-Schmidt this and blah, blah, blah. But they also know that whatever that orthogonal projection is, which is, let's call this the subspace W, then this would be the projection onto W of Y. That's how they write it? Okay. And what they did in the course notes is they went, okay, so here's W, which is a plane, and here's Y, and we project W onto Y with the right angle like that. And this bit here, and this point here that's actually on the plane is the projection onto W of Y. And this journey just here from Y to the projection of Y has to be orthogonal to W, because that's what an orthogonal projection is. If we were doing like a 30-degree angle projection, then the angle between this and the plane would be 30 degrees. But we're doing an orthogonal projection. Not that they ask you to do any other kind in Maths 1B. I just wanted to point out why it's got the word orthogonal on it. If you don't do any other kinds of projections, why does it have an adjective And it's because it's technically possible to do other kinds of projections. Okay, so this vector that goes from the projection outwards to y. So when you subtract two vectors, it gives you the journey between them. So this is from the projection back to y. That has to be orthogonal to the entire of W. That's the word orthogonal. And so therefore, that means that when you dot this with x, you should get 0. And when you dot this with lambda, you should also get 0. All right. Cool. And the final trick that they pulled is to say that this and this, like this vector, whatever it is in the subspace W, so it must be A times X plus B times lambda for some possible values of A and B. So projection onto W of Y is A times X plus B times lambda. Well, my lambdas are getting worse and worse for some A and B, because it's in the span of X and lambda, and so it has to be a combination. And so, just I'm glad for myself for doing this because it makes me feel better. But what I'm going to do is first I'm going to expand out this dot product. Zero. And then they replace this with AX plus B lambda. But I'm going to make it even better because I really don't like those minuses. Oh, this is an X, this is a lambda. Sorry about that. Expanded this out with a lambda. Actually, I just need to pause for a moment and go, that's kind of cool. Look at this. The dot product between the vector y and a vector in the plane is the same as the dot product between its projection and the same vector in the plane. So if I pick any vector in the plane, that always happens. If I have any vector outside the plane and its projection, the dot product of this with anything in here is the same as the dot product of this with that thing in there. If you pick something in here and do the dot product with both of these things, it will give you the same answer. Yep.
This form 24, it's gonna look like no, that's the one. It kind of looks like eigenvalues.
It does look a bit like eigenvalues, doesn't it? Probably there is a way of doing it quicker with eigenvalues, but I'm not sure how to do that off the top of my head. I do know that people do kinds of regression with eigenvalues. So it must be possible because I know it's done. People do it. Yep. If you know how, then go for it. Well, there's a button over there which turns it on, but I don't know if we can turn it off. Yep, I don't think that turns, I think that just turns it on more. You've turned the lights off. That's all good. I wish it was. I think it's still set for 43 degrees, which was yesterday's temperature. If I had jumpers to give you, I would give them to you. Okay. So that feels like a lot of work and I need to summarize it, but we're here at this point and there's one more step to go, which is we need to put the AX plus B lambda y dot X is ax plus b lambda dot x, and y dot x is ax plus b lambda, y dot lambda dot lambda. And so I have y dot x is ax dot x plus b lambda dot x, and y dot lambda is ax dot lambda plus b lambda dot lambda. I did it again. Lambda dot lambda. Okay. And are you ready? Look, this, we had a list of y's and a list of x's, and if we do this dot product, we'll have a number. We have a list of x and the list of x's again. We do this dot product, we'll have a number. Do this dot product, we'll have a number. We have two equations and two unknowns. It's a pair of linear equations. I can solve those with row operations or inverse matrices or whatever. Yay. So that's how it's done. So I wish in this course they hadn't done this bit and they had just done this bit and just literally given you some data and said, do the orthogonal projection. And then ask Desmos what the linear regression is and note that it's the same answer. That would have been a really good assignment question, but they didn't do that. So what they actually did is they did something like saying x is a list of, like, I don't know, some numbers, and y is, no, wait. I will write those again in a second, but they wrote something like 1, 3, 2, 5, 3, 2, 4, 7, something like that. And then said, find the line of best fit via orthogonal projection. No, good point. You said, isn't x dot x and lambda dot lambda equal to 0? That would be true if this was an orthonormal basis, but it's not. Because if you were, you're right, if you were going to do orthogonal projection, you would have to have an orthonormal basis, but you would have to make it from here with the Graham-Smith process. And so, you know, no such luck. They are not currently orthogonal to each other. Wouldn't that be nice? We do know what lambda dot lambda is, because lambda is all ones. And if you have all ones dot all ones, you just get 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. So you get how many ones there are, which is n. And so this number here ends up being the number n, because it's 1 times 1 plus 1 times 1 plus 1 plus 1 times 1. Yeah. And in fact, this one ends up being the sum of the values of x, because you have x1 times 1 plus x2 times 1 plus x3 times 1 plus x4 times. So that'll be the sum of the values of x. This is the sum of the values of y. That is the length of x squared. And this is, well, the dot product of y and x. Not much you can do with that. But yeah, so this is the sum of the x's. That's kind of cool. So you can do a shortcut with some of these things. So this means that the vector x would be 1, 2, 3, 4, and the vector y is 3, 5, 2, 7. And we know just for our things, the vector lambda is always 1, 1, 1, 1. Good with that. And so y dot x is 3 plus 10 plus 6 plus 28, which is 38 plus 9, which is 47. Sure. It wasn't going to be pretty, I just made up a number. Trivia, 47 is a number that when they make Star Trek episodes, almost always if they say a number as part of their technobabble, it will have a 47 in it. It's one of their little in-jokes. It's the prime number directive. So x dot x is 1 plus 4 plus 9 plus 16, which is 30. That's cool. Okay. And what else do we need? We need lambda dot x is 1 plus 2 plus 3 plus 4, which is 10. And lambda dot y is 3 plus 5 plus 2 plus 7, which is 17. Because that's 10 and that's 7, yep. And lambda dot lambda is 4. Sweet. And so I want y equals ax plus b, so that, all right, here we go. We've got y dot x, which is 47, and a times x dot x, which is 30a, and b times lambda dot x, which is 10b. And I also want lambda, y dot lambda, which is 17, and x dot lambda again, so that's 10a, and lambda dot lambda, which is 4. And now I have 2 equations and 2 unknowns. Should totally be possible to figure out what a and b are, theoretically. So, 30, 10, 47, 17, no, 10, 4, 17. And I have to solve that. Not a fan, honestly. I can do it. I'm going to divide the top row by 10 and the bottom row by 10. And then I'm going to take row 1 is row 1 minus 3 of row 2. And so that gives me this. So 3 lots of 0.4 is 1.2, so that'll be minus 0.2. And 3 lots of 1.7 would be 3 plus 5.1. I should have known that, actually. And so we take off 5.1. So 4.7 to 5.1 is minus 0.4. Cool. And then I'll have to do row 2 is minus a 0.2 of row 2. It's actually turning out a lot better than I thought it would. 0, 1, 2. And then row 3 is row 2 is row. That was row 1, David. Row 2 is row 2 minus 0.4 of row 1. I'm sorry that I've done my row operations upside down. You're allowed to do that. It's going to swap the rows at the end. And so I'll put on this, and 0.4 times 2 is 0.8, and so this will be 0.9. Yay! That was fun. I mean, if I was in an exam, I'd use a calculator. It's good for you to do mental arithmetic. And so this was A and B. And so A is 0.9 and B is 2. And so therefore the line is y equals 0.9x plus 2. Cool. I just want to check that in my mind. I want to see if I believe that this is what it should be. So what have I got? 1, 2, 3, 4. No, I'm going to need. And then 1, 2, 3, 4, 5, 6, 7. So we have the point 1, 3. Two, 5. And 3, 2. And 4, 7. And my line was 0.9x plus 2. So that's got y-intercept 2. And the slope is just under 1. Oh yeah, that's not too bad as a line of best fit. Magic. Yep.
Is there any way to get a negative slope, or like, is there any sanity checks you can do that if you have some certain answer or don't make a mistake?
I just draw a quick sketch of the graph.
Yeah.
Other than that, not really. If this point wasn't there, I'd expect it to have negative slope, probably. That looks like the best line of best fit there. Yeah. Wow. Cool. And it did. The other thing is that if looking at that, it is on average, the Y values are increasing. Like without that point, the Y values increase as the X values increase. And so the slope should be on average positive. That's what I'm expecting. Actually, I really like I'm happy with that example. It was a good example. But what you do need is this to be written down somewhere, or somehow to be able to figure it out on the fly, which wasn't fast, let's say. So it seems to me that the amount of effort it takes to figure this out on the fly is not worth it in an exam. And so I'd write it down somewhere. I have no idea if it's going to be in the exam, like honestly. It doesn't feel like an exam sort of thing to calculate that. Sorry? Yeah. Doesn't feel like an exam sort of thing to do that calculation. Maybe. However, I will say, by us talking about all these things, there was some good stuff in there that makes us understand everything else just a little better. So has anyone noticed anything in there that they went, oh, I could use that for something else and not necessarily regression? Anything that I did that you go, I want to keep that trick for later? You don't have to say something, but. I just want to say that's good practice. Every time that you watch any teacher do anything, even if you're not planning to take any of the things they're doing and do them yourselves ever again, like you just say, I'm not going to do linear regression in my exam, so I don't need to know any of that. Don't have that attitude. Go, there must be something that happened in that discussion that is useful that I can take away for the future. For example, you may go, oh, well, I can do my row operations and get the reverse of the identity, and that's okay if it appeals to me on the day. Or you might think, David, that was ridiculous. I'll just do it the normal way. Whatever. But you get to decide whether you like that procedure or not and choose the one that you like best. And you can notice that that you can expand out dot products. It may have been something that you forgot. And so therefore in doing proofs, maybe expanding dot products is a useful thing. Yeah. And you can keep in the back of your mind that dot producting with the vector that's all ones is the same as adding something up. And that is something that may come back to you if you do more statistics using linear algebra, is that anytime there's a sum, you can replace it as a dot product with the lambda vector. It's kind of a cool thing. Do you know what occurs to me? This process just here of calculating all those things and doing the row operations is not shorter than actually doing the Gram-Schmidt process and the orthogonal projection. Anyway, yeah.
Projection of line and number two is considered linear projection. If we did both involving projection of line, is it better to do it as the left-hand side or as the right-hand side?
So I'm going to repeat that question. If you're doing proofs, is it better to leave it like this or like this?
So practice questions.
Okay, so some of the practice questions, it was one way or the other, and then that tells you that the situation will be different. Sometimes one of them is more useful than the other, depending on what you want to do today. in general, it is easier to work with this if you don't know what the vectors are. Because it's hard to figure out the projection if you don't have the actual orthonormal basis to work with. Yeah, so that would be my instinct. Because if you don't know what the vectors are, then you can't figure out the orthonormal basis, and therefore you can't figure out what the projection is. And so this would be easier in a proof. On that note, do you want to talk about some of those proofs? So if you have any examples of algebra-ish proofs that you've been asked to do and you want me to talk about them, let me know. But I did one yesterday in the Maths Learning Center. I was talking to someone, about there's a theorem that goes that if A is symmetric, then eigenvectors with different eigenvalues are orthogonal. I have no idea if I'm going to be able to prove this off the top of my head, but it is a thing that is provable. So one of the, just to let you know, for an ordinary matrix that isn't symmetric, or it could be symmetric, but for just a regular matrix, eigenvectors with different eigenvalues are linearly independent. But for symmetric matrices, eigenvalues with different eigenvalues are not just independent, but orthogonal. Okay. Okay. So my advice for proofs is that twofold. Well, I may have other advice along the way, but proofs are about definitions. You have to use the definition somewhere, or use another theorem somewhere. So proofs are about referencing pre-existing information, and that's usually definitions. And so a useful strategy when trying to think of a proof is to think of the definitions of things. That's my first piece of advice. And in fact, that is almost totally my whole piece of advice, other than you should keep the goal in mind. But not all the time, just check with it regularly. So know what you've got to begin with and know what you're aiming for, and then know what the definitions of those things are and try and connect them up. That's the goal. And you can work from either direction if you need to. So A is symmetric. So, and then we can put a definition of what that means. Having eigenvectors, we need to have a definition of that too. In fact, just before, I'm not going to start doing my proof at the moment. Just let me this is stuff that I'm going to do definitions. A is symmetric. I should have just put the box around there, sorry. So what does it mean to be symmetric for a matrix? That would be a question we need an answer to. Yep. So the transpose and the matrix are the same. Is that what you said? So you may have in your mind a different definition. Like you go, oh, I know it's symmetric if the diagonal entries, like opposite ones, are the same. That may be what's in your mind when you're checking if a specific matrix is symmetric. But for the purposes of a proof where you don't have the matrix in front of you and you don't have any of its entries, this is the algebra version of a matrix is symmetric. So a useful thing to know is that there is things that you know about. When you have a word and know what it means, there's a meaning of it that you would use if you have an actual matrix in front of you. And there, because you wouldn't literally transpose the matrix and go, oh, look, it's the same. That's not what you would do to check if something was symmetric. You would just see if the off-diagonal elements were equal to each other. But in algebra, you need something that doesn't require you to know any of the individual elements. And that's what this is. And so a useful strategy for algebra proofs is to somehow write your definition so it doesn't reference the individual elements of the vectors or the matrices. Okay. What's an eigenvector? That's something we need to know. So I'm going to get one of you to tell me. Yep.
The vector such that if you do A times B equals to some a scalar multiplication.
So A times V is like that. Yep. And also technically eigenvectors aren't supposed to be zero. Eigenvalues are allowed to be zero. And so it's a vector so that this happens. Yep. And what's an eigenvalue? Okay, so you're saying, cool, you've said you're about to say, oh, you do the determinant of the lambda I minus A and you solve that. That's how to find an eigenvalue, but it's not what an eigenvalue is. An eigenvalue is the number in this equation. So the number just there, that's an eigenvalue. The vector in these two positions, that's an eigenvector. So the definition of eigenvalue is a number lambda so that AV is lambda V, or some V. Okay. So a good thing to know is if you're going to do proofs, this is the most useful piece of information about eigenvectors and eigenvalues. The AV is lambda V. And eigenvectors, eigenvalues, orthogonal. We need to know what orthogonal means. Yep, orthogonal means right angle. The word literally means right angle. Ortho means correct, i.e. right, and gon means angle, as in hexagon. So it's the correct angle, as in the right angle. It literally means right angle. That is true. But what's the algebra definition of orthogonal? Dot product is zero. So V times W equals zero, something like that. So both of those things that we've talked about, every one of those things has two ways to think about it. There's the definition, which has like algebra equations. And then there's the with no reference to anything. And there's also the way to find it. And there's also what it means geometrically. So orthogonal has a meaning geometrically, but it also has an algebra definition. And eigenvalues have a way to calculate them with the determinant of lambda I minus A, but they also have a definition of what they are. So yeah, so keep it in your mind. So what we would like to do is start with a symmetric matrix, think about eigenvectors that have different eigenvalues, and somehow prove that those two eigenvectors with different eigenvalues, the dot product is zero. So this is telling me a little bit of the shape of my proof. I want to make a statement like this at the end, that V dot W is zero, which means I need to tell my reader what V and W are, and they are going to be eigenvectors. So that I've got my proof to begin with, and it will be let V and W be eigenvectors of A with different eigenvalues. And we should give those eigenvalues letters as well, and we know they're different. So I could call the first one lambda, and I'm going to call the other one mu. But you could have, if you want to call them V1 and V2 and lambda 1 and lambda 2, if that made more sense to you. But I'm a big fan of using more letters. Mu is the Greek letter after lambda because it's LM. They might not be in that order in the Greek alphabet though, but they are in the English alphabet. Okay, so cool. And so the thing we know for sure is that AV is lambda V and W is mu W. Because that's the definition of what it means to be eigenvectors with those eigenvalues. So the first thing I will write after I declare something's are eigenvalues, I'm going to write this down in the hope that it is helpful, because that's what they mean. And then my goal, somewhere at the bottom of my page, so I'm going to guess that my proof's going to take about this much space. And if it doesn't, oh well, I'll just have to make more space. But I'm going to say, therefore, V dot W is 0. Oh, sorry, that's not an underlined 0. It's just a plain 0 because it's not it's a number, not a vector. That's my goal. Somehow to get from here to here. Cool. Oh, just a second. So V and W are orthogonal. That will be my final line in the proof, because they said show that they're orthogonal. So my final line in the proof should have the word orthogonal in it, so that the person reading it can tell that I've gotten to the end. Okay. So somehow I have to use these two, and the A is going to have to disappear somehow and get to here. Okay. Oh, maybe. Not sure. My naive thoughts are to do the dot product of lambda V and mu W, because I should be able to multiply both sides of this by lambda and mu, and it would still be true. So what I'm thinking is, this is my thought. I can't. It's done. This is my thought. It might not be a good thought, but just temporarily, I'm thinking that that if I multiply both parts of this by lambda and mu, it would still be 0, right? And these are in those equations, and that could work. Yeah. I'm just going to put this over somewhere else and come back to that in a minute. Lambda V dot mu W would be the same as AV dot AW. Yeah. And I have to use the fact it's symmetric somewhere. I haven't used that yet, so I'm going to have to get an A transpose in here somewhere. That's okay, because dot products are transposes. The dot product of two vectors is the same as the transpose of the first one times the second one. Like this is a fact that I know, that like U dot V is the same as U transpose times V. And that one's a row vector and that one's a column vector. So when you do matrix multiplication, it works out to the same as the dot product. Okay, so this is AV transpose times AW. Okay, cool. And the other thing I know about how transposes work is that when you pull the transpose inside a multiplication, you have to switch the order. And so this becomes V transpose A transpose AW. Like A, B transpose is the same as B transpose A transpose. So you can expand transposing across matrix multiplication, but only if you reverse the order. Okay. Okay, so I haven't actually used the fact that it's symmetric yet. I created a transpose so that I could use the fact it's symmetric. I have the fact that symmetric is that I have that A, this is A. All right. This is so exciting. Okay. Watch this. AW is mu W. And that's a number, so I can bring it all the way out the front. And AW is mu W. And so I've got mu squared V transpose W. Hoo-ha. David, why are you smiling so much? How does that help us? Just watch. You're ready? You know, if I switch the order on this, then the V would have been second, and I would have ended up with lambda squared W transpose V. So lambda V dot mu W is the same as mu W dot lambda V, which will be working out to lambda squared W transpose V using the same reasoning. This is a trick you can use when you're doing proofs. If you think that it will work exactly the same way, but you've just moved the things around, then you can move the things around. I can just say, well, it's the same working. You don't have to put the bit in the middle if you don't want to. All right, here we go. See this and this, they're the same. But you know, they're the same thing, which means this and this are the same. Yeah? So mu squared V transpose W is the same as lambda squared W transpose V. Yep. But that's mu squared V dot W is the same as lambda squared W dot V. But W dot V is the same as V dot W. So I'm just going to do this. Okay. Right. We're so close. And so mu squared minus lambda squared. So I'm going to put this over this side. And then I'm going to factorize it out. I'm going to get this. But mu and lambda aren't the same, so this number's not zero. So I can divide by it. Mu is not equal to lambda. So mu squared minus lambda squared is not zero. And so therefore V dot W is zero. Hey. Yay! I wouldn't expect them to have this proof in an exam. This feels like too much divine inspiration. But I don't know what kind of psychopaths are writing your exam. So, who knows? Now, sometimes I'm acting when I do these proofs in front of people, but I really didn't know how that proof worked. Now, you can't tell that I'm acting by saying that I'm not acting, but whatever, I really am not. So I really didn't know how that would turn out and whether it would turn out. And that's just how proofs work. Most proofs that they give you in exams, literally writing down the definitions at the beginning and the end gets you very close to the answer. Proving that things are subspaces work that way. So I just want to do the little debrief there, the post-game debrief. So I wrote down, well, I thought you don't have to write this down if you're in your exam, but if it helps you to write it down, then do so. But I thought about the definitions of the things, and I thought about what I was aiming for. And in order to make this statement, I would have to tell the reader what those things were. And so I went back at the beginning and said, let them be eigenvectors. And then I wrote down the definition of what it meant to be an eigenvector. And I wrote down what I was aiming for. And I stared at the information that I had and hoped that I would think of something. And I went, okay, well, I've got a v dot w here. I do have some things with v and w in them. Why don't I dot them together and see what happens? Now, it might have been okay to just directly dot av dot aw and just work from that directly. I didn't necessarily have to start with this. Actually, you know what? That would have been, I could have not put this first line in. That would have been fine to just start with the av.aw because that's here as well. That would have worked too. So I could have done the proof from here. I could have started in that spot and it would have worked fine. And then I did what I could do. I did the things that I knew, and I thought of new things I hadn't thought of before. And then tried my very best to get it to a point where I could use the other information I had. Yeah. I don't know, did they show this proof? Yeah.
We could propose, if there is a u squared minus 1 squared and different result, but they can be different instead.
You're right. What if one was minus the other? Ooh. So what if mu was minus lambda? That would be a problem, wouldn't it? Well, that sucks. So if I was in an exam and in the last minute, I realized that my proof didn't work properly, I would write a note to say, I have noticed that this is not necessarily true, but I haven't got time to fix it. And I would literally write that on my exam, because then you could prove to the person reading it that you knew it was wrong. And that might be, they might give you 1 mark out of 5, 1 extra mark out of 5 that they wouldn't give you because you showed that you knew it was wrong. And it could make all the difference between like a distinction and a high distinction. So just, if you ever notice something is wrong and you don't have time to fix it, write down that you know it's wrong. I just want to point that out as a piece of exam strategy. I don't know how to fix that at this time. I was so proud of my proof. I've got it. Maybe. I think I can fix it. I can fix it. Okay. What if I didn't have, the thing that caused this square here was having 2 A's in this formula? What if there was only 1 A in there? Then I wouldn't have the squared. So what if I had AV dot W? Yep. And so that's lambda V dot W. That's great. But AV dot W is AV transpose times W as matrices. And that's V transpose A transpose W. And that's V transpose AW, which is V transpose mu W, which is mu V transpose W, which is mu V dot W. And so therefore lambda V dot W is mu V dot W. And so lambda minus mu V dot W is 0. And now I can be sure that lambda is not mu and therefore that's not 0. That's lambda is not equal to mu. Therefore lambda minus mu is not 0. And therefore V dot W is 0. Fixed. Awesome. Like, yay. So cool. Anyway. Gosh, I wish I had a fairy in the exams to sit on my shoulder and tell me that I've done something wrong so that I can fix it. Wow. Okay. Okay. So this is all gone now, but I'm going to keep it there for historical reasons to remember where we've been. And so, and therefore, B and W are orthogonal. Right, that's much shorter. And so I reckon a lecturer might possibly include such a thing. To be fair, we didn't think of the short version until after we did the long version. That's how it works sometimes. Yep.
Then W has to be, they can't be the negative of each other because they have to be independent. And then the first method works.
No, because if vectors are negatives of each other, then they have the same eigenvalue. Yes, but yet you could do that. But our problem was that the eigenvalues might have been the negatives of each other, not the vectors being negatives of each other. That's the problem. Yeah, but it was the lambda and the mu that were minus each other, not the v and the w that were minus each other. That wouldn't be because the w's only there once. The fact that it's a negative will actually make this different to this. I don't think that will fix it. Sorry. I'm not using it. I'm just randomly dotting vectors that I've got on my page together to see what happens. Oh, yeah. So you're saying, why am I allowed to just not have the two A's in this? Because I'm not saying that this is equal to that. I'm saying that this is equal to this, but it's also equal to that. And in this proof, I went, this is equal to this, but this is also equal to that. And so what I did is, because I was working with two of the same thing that worked out to two different answers, it doesn't matter if I change the thing I start with, as long as both of the things I change it to go to different answers. Yeah, so what I was trying to do is copy the vibe of this proof where I started with the same thing twice and then went to different places. I'm just going to pick a different thing to start with and go to two different places. And they're different to the places I went to last time, but it doesn't matter because as long as they're different to each other, that's all right. Yeah. Yep.
It's example, the way of starting from the end, and then try to get to where we start with, or what we begin with. Is this a valid goal, a valid method?
Yes. So looking at what you're aiming for and trying to link up to that from the beginning is a valid method for many proofs, especially proofs in Maths 1B. Some proofs you don't know exactly what you're aiming for, and that makes it harder. But subspace proofs are like that, where you prove, suppose U and V are both in W, therefore you want to prove that U plus V is in W. So in a subspace proof, the theorem, the definition of subspace says that if U and V are in W, then U plus V is also in W. That's how the definition works. Your proof, in general, will begin by saying, suppose this, working, 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 therefore this. And if you write down, based on the subspace you've got, there will be a rule for deciding whether a vector is in W. If you write down what both of these are and what both of these are and stare at what you've got, you should be able to connect them together. Yeah. And so it's a very useful way of at least beginning doing a proof. There are lots of different kinds of proof methods. If you choose to do it by contradiction, that's a whole other thing. But my first guess is to try and do this. This is called a direct proof. And a lot of the definitions in algebra are chosen specially to make direct proofs easier. Because definitions are often chosen by mathematicians to make proofs easier. Yeah. Is there a sufficient amount of advice in there to make you feel like I've dealt with algebra proofs? Are there any other proofs you've seen that you want me to talk through? I have talked about this a few times across the years, so if you want more, then go and find it or just come to the Maths Learning Centre. So, that's what it's for. All right, we've got half an hour. I'm just going to have some water while we ponder what we are talking about next. Okay. We don't know which one of the ons. No, that's the thing that senses if there's people in the room. Sorry. I am very cold as well. Actually, this t-shirt is a reference to a scene in a book called Men at Arms by Terry Pratchett. And in that scene, there's a troll and a dwarf stuck in the Futures warehouse, which is a frozen warehouse. And trolls being made of stone, their brains work faster when they're colder. And so he starts doing maths by writing in ice on the walls. The very end of it is in pure maths with no numbers, and there's just an equal sign at the end. And the dwarf is saying, equals what? Anyway, and so this, I feel very authentic wearing this because it's so, it's a book. It's called Men at Arms. It's a Discworld book by Terry Pratchett. It is the second book featuring these characters. So those two characters aren't in the first book because the dwarf in the first book dies and Atreus doesn't arrive until the second book. Sorry. Sorry, everybody. Oh no, is that? Oh, I don't remember. There's 41 Discworld books, and I don't always remember what order things happened in. Yeah. 41 Discworld novels, and there won't be any more because Terry Pratchett died in 2015. Okay. Moving on, linear transformations, multivariable worded questions, not necessarily multivariable, but like related rates sort of questions where you're trying to connect together the rates of change of things. Let's vote. Linear transformations, hand up. Calculus. Oh, come on, it's 3 and 3, undecided. Okay. I have got lots of videos on related rates. Well, let me just mention what they are. So related rates is one of those questions where it says you've got some situation and there's something that's changing with time. And it says, if you know the rate of the water flow, what is the rate of the height changing? Those sorts of questions. Yeah, and in 1M if you did 1M as well. They did. I'm gonna make a couple of pieces of advice, but not necessarily do the whole thing. Okay, and then we'll still talk about linear transformations. There will be time. All right. Calculus. You can do them in a multivariable way. Is it in Maths 1B?
Something broke with the water and contaminated it.
And the oil wells in Maths 1B, right? 1A? Maybe it's not in 1B. I'm sure we had the cone with the water in this course. That was 1A? Okay. Then 1A. It might, okay, so there might be multivariable vibes for those things, maybe. You might have to find the example. If you find the example before I finish with linear transformations, then we can still do it. Okay. Come back to that. Okay. Now, what you asked for specifically, person who asked this, who I can't, it was somewhere in the middle there, was you're okay with probably what the meanings of them are and the definitions of them, but like what to do when you're presented with something. And did you find an example? I'll come over there. So I'm going to do this problem, a similar problem live, and we're going to say any of the random facts about linear transformations we need to know along the way, rather than me summarizing at the beginning. Just warning you, that's what I'm going to do. Sure, you can call someone, but it's too late now. Okay, so here's my problem. And I'm going to call it G because that's fun. G, which sends our yeah, we're just going to do R3 to R3. Wait, just bear with me. I'm going to go to R2. Sorry for changing the question in the middle of it. Making up problems so that they work is a whole other thing. So just bear with me for a second. Okay, G, which sends R3 to R2, is a linear transformation with these three pieces of information. Find the standard matrix for G. This is the kind of classic question we're talking about. Okay. So this is a classic. And as you said in the notes, the vectors that they had in these positions were 1, 0, 0, and 0, 1, 0, and 0, 0, 1. Okay. I just wanted to make one final check in my mind just to make sure this is going to work out. Yeah, okay. Pretty sure. I just want to say there's no particular reason you have to use whole numbers for everything. It's easier to think of questions as a lecturer if I put whole numbers in to begin with. It's just, I did it in, yes, it is in R3. I'm not going to be able to solve the problem unless I have 3 different inputs. So yeah, that's what you're asking. Yeah, so because the domain is R3, I won't be able to find the standard matrix without at least 3 inputs. Yeah. So if it went from R2 to R3, you would only need 2 inputs to solve the problem.
The dimension of the
No. Yep. That's a good question. We should answer that question. So let's think about some things before we actually solve this problem, because it's brought up some questions in our minds. So useful piece of information. This is still ordinary function notation that you've seen before when you like f sends R to R, that sort of thing. So this is called the domain. Same as with ordinary functions. This thing may not be the range. It's not technically, it may be that your linear transformation doesn't in fact cover the whole of R2, in which case the range is smaller than R2 and something else. So there is in fact a word for what this thing is called. If it's not the range, this thing is called the codomain. In case you were wondering, they do not tell you this word in Maths 1B, but I think it's worth noting because you tried to talk about it and you didn't have a word for it. And so that's why I wanted to give you the word in case you were wondering. But sometimes you will be able to cover the whole of this, in which case it's the range, but sometimes you won't, and the range will be smaller than that. Okay. So the way linear transformations work is that it is always possible to write your linear transformation using a matrix. So I'm starting with vectors in R3 with 3 coordinates as columns, because it's easiest to do this with your input vectors and your output vectors actually being columns. So even if a person gave you this question and wrote them as rows, you would still write them as columns when you do the actual working. Yep. So it takes vectors with 3 coordinates and it spits out vectors with 2 coordinates. And it does that by multiplying by a matrix here. That's how G does its job. And all linear transformations, no matter how they're described to begin with, can be rewritten this way. So here's the thing. If I want to multiply a matrix here, it's going to have 3 positions here so that I can multiply by the 3 positions here. So I'm going to need to have 3 positions there because this times that has to be possible. But if I want the answer to have 2 coordinates, I'm going to have 2 rows. This row will produce that answer, and this row will produce that answer. So it says I want a standard matrix, and that is the matrix I'm looking for. And the matrix I'm looking for will have 3 columns because I started in R3, and each of those columns will have 2 coordinates because I'm finishing in R2. Yeah. And I don't even think about that with numbers until I draw this picture and then I go, aha, it's a 2 by 3 matrix. But yes, it will always be this by that. But again, I have extremely bad left-right confusion. And so if I draw the picture, I can get it right. Okay. So my final answer will be this matrix here. That's what my goal is. Okay. There is a magic trick. Yeah. There is a magic trick, and the magic trick is this. I know that when I do matrix multiplication, I can do like and add them up and get me this answer. But I also know that I can do this whole vector times that number, and this whole vector times that number, and this whole vector times that number, and add those up, and it also gives me the answer. When I do matrix times column vector, what I'm doing is a linear combination of the original columns. I can think of this, I'm just going to draw it again. This isn't necessarily useful at, in direct terms at this time. I just want to tell you. I can think of this as number times that plus number times that plus number times that. Like if this is A, B, and C, I'll get A times the first column and B times the second column and C times the third column. That's what matrix multiplication does. That's one of the ways of thinking about matrix multiplication. That multiplying by a column does a linear combination of the columns. By column equals linear combo of matrix columns. That's a useful thing to think. So I want this matrix, which means I want its 3 columns. And that's why I need 3 pieces of information to begin with, because I'm going to need to find 3 columns for my matrix. I need these 3 columns. And if I want just the first column, then what I should put in this spot is 1, 0, 0. So that'll be 1 times the first column, and 0 times the second column, and 0 times the third column. And so that will be the fifth column. That will be the first column. And if I multiply by 0, 1, 0, that will be the second column. And if I multiply by 0, 0, 1, that will be the third column. And so therefore, what I need to know is what G does to 1, 0, 0, 0, 1, 0, and 0, 0, 1. So therefore, G of 1, 0, 0 is the first column. And G of 0, 1, 0 is the second column, and G of 0, 0, 1 is the third column. So I have now turned my question into, it did used to say, find the standard matrix for G. And now the question is, what is G of 1, 0, 0, and what is G of 0, 1, 0, and what is G of 0, 0, 1? That will answer my question of what is the standard matrix. Okay. So I have to use the information I've got to somehow figure out those 3 answers. There are multiple ways to do this. So one way is to stare at these in the hope that I could somehow create from these vectors 1, 0, 0, and 0, 1, 0, and 0, 0, 1. I can make 0, 0, 1, 1. But that's a good start. Let's try that. So G of 0, 4, 4 is 8, 2. And so therefore G of 0, 1, 1. Dividing this by 4 will mean dividing that by 4 because that's how linear transformations work. If you multiply a input vector by a number, then you also multiply the output vector by the number. And I'm going to multiply it by a quarter. Oh, it totally is. Thank you. Okay. And now let me see. Aha. If I do this one minus, that's not helpful, is it? Curses. I thought that would help. Okay. Well, the middle one, if I took this off of that twice, I'd get 0, 2, 1. That'll work. So G of 2, 2, 3 minus 2 lots of 1, 0, 1 will be minus 1, 5 minus 2 lots of 3, 1. And that's the same as G of 0, 2, 1. That is, so what I've done here is I've tried to combine these somehow by getting rid of, to try and make one of these coordinates go away, because I need to get more and more zeros, basically. So I'm going to make the first coordinate go away, and that would mean I have to take off 2 of these. And so that's how I've done that. And then I've done the same combination of the answers. And so 1 minus 2 lots of 3 is minus 7. 5 minus 2 lots of 1 is 3. And now if I do this minus this, I will get 0, 1, 0. And so I have the middle column of my matrix. So this is the sort of thing one could do if you wanted to fiddle around with it in that way. Yep. So you can multiply by a number, you can divide by a number, you can add them together, you can subtract them, that's it. Yep, exactly the same stuff as row operations. And that's a very important and deep observation you have made there, that they are the same as row operations. Okay. So I do know that if I did my 0, 2, 1 minus 0, 1, 1, then that would give me G of 0, 1, 0. And 0, 2, 1 was minus 7, 3. And 0, 1, 1 gave me 2.5. And so I get minus 9 and 3 minus 1/2, which is 2.5, which is 5 halves. So I now know what the middle column is. Yes. But that's okay, cool. Now that I know what 0, 1, 0 is, I can do this minus 0, 1, 0, and that gives me 0, 0, 1. Yeah, okay. So 0, 0, 1 is G of 0, 1, 1 minus 0, 1, 0. And so G of 0, 1, 1 was 2.5. And 0, 1, 0 was minus 9, 5 halves. So 2 minus minus 9 is 11, and 1/2 minus 2.5 is -2. It's my third column. Awesome. Let's see what else I've got. Oh, yes, I've got 1, 0, 1. If I take off 0, 0, 1, that gives me 1, 0, 0. Yeah, yeah. E of 0, 1, 0, 0 is G of 0, 1, 0, 1 minus 0, 0, 1. And g of 1, 0, 1 was 3, 1. And 0, 0, 1 was, I just did that one, didn't I? 11 minus 2. And so I've got minus 8, 3. First column. And so therefore, the standard matrix for G is first column, second column, third column. Yay! So you can do that if you want. And it should be, if they gave you something like this in an exam, it should be possible to cobble them together in that way. And it doesn't necessarily have to be in that order, just whatever occurs to you. And I should really just check if my answer works. So just to be clear, so just to check, minus 8, 3, minus 9, 5, 2, 11, minus 2 times 1, 0, 1 should come out to 3, 1. So let's see. Minus 8 plus 0 plus 11 is 3. Awesome. And 3 plus 0 minus 2, 1. Yes. If I wanted to be consistent, I should check them all, but that'll do. This won't check my middle column because there's a 0 there. So should probably do at least one more to feel better about it, but I'm just going to stop there.
Given G of 2, 2, 3, and then you have another column.
Yeah, so G of 2, 2, 3, I would probably feel more comfortable with it telling me useful information. Let's do just a second. I will do one more just in case. Yeah, that'll make me feel better because it doesn't have a 0, so it will involve all 3 of the columns. So let's see. Minus 16, minus another 18. It's minus 34, plus 33 is minus 1. Is that what it was supposed to work out to be? Yes! Oh! And 6 plus 5 is 11. Minus another 6 is 5. Yay! Okay, awesome. So cool. I don't know if I could survive in an exam without being able to yell when I think I've got something right. You can see me in a second. I need to excuse myself to just do a little happy dance outside. Anyway, I'm much more vocal about those things than I was when I was a student. Okay. So I just want to say there is another way to do this. If you didn't want to trust your brain to just happen to think of the right combinations of the input vectors to get those things, what you want, there is at least 2 more ways to do this. But what you're aiming for, you need a linear combination of these 3 things that produces 1, 0, 0, and 0, 1, 0, and 0, 0, 1. So, or need linear combo of 1, 0, 1 and 2, 2, 3 and 0, 4, 4 that makes 1, 0, 0 and 0, 1, 0 and 0, 0, 1. So I need to solve the equation A times this plus B times this plus C times this equals this. And the way to solve that is to do a matrix. Like I need like something times 1, 0, 1 and something times 2, 2, 3 and something times 0, 4, 4 comes out to 1, 0, 0. And if I row reduce that, it'll tell me what A, B, and C is, and that's the correct combination that I need. But I also need another combination that produces 0, 1, 0, and another combination that produces 0, 0, 1. And so I can just attach all of those answers to the end because the row operations that do this bit are based on this bit, and the row operations that do this equation are also still based on this one. So I can just make a giant matrix and do them all at once. It is 100% the same method you use to find the inverse matrix. Yeah. So what I'm doing here is finding the, because to figure out what A, B, and C are, I would need to get to here. And then whatever this is the A's and the B's and the C's. This here is the inverse of that matrix. Yeah, and so if I did those row operations, it would do the job for me. I will show you because I just really need to make sure it works. So 1, 2, 0, 1, 0, 0, 0, 2, 4, 0, 0. So I'm going to do row 3 minus row 1, and that will get me an extra 0 there. Yes, thank you. And row 1 and row 3 minus row 1 is this. Have to do that whole row, right? Thank you. That would have been a disaster. And then I've already got a 1 here, so I'd probably move that up, or I could divide that one by 2, but that would make fractions, so I'm going to move it up. But I might just do the row operations now and move it up later. So I've got 0, 1, 4, and I'll take off 2 of this off of that one, and so that would be there minus 8. This minus 2 of that would be 2, 0, 2. And I'll do the same thing here. And then I'll do, no, that's a 0, sorry. What are you doing, David? And then I guess I'll divide this one by minus 4 to make the one that I need. I'm very sorry that I am not doing this in the order it should be, but you'll cope. I'm very distressed that I've got a quarter there where I shouldn't have one. I've done something wrong. Oh no, that's okay. Everything's fine. Everything's fine. The standard matrix is not in this picture. All good. Everything's fine. Okay, and we've got half, and then I'll do plus 8 of these. So we need to keep that middle row. So obviously they wouldn't get you to do this in an exam, like it just takes ages. Or they'd have more zeros in their vectors. But if they had more zeros in their vectors, it would be easier to see how to just make them out of each other. So I'm going to do this row plus 4 of that one. So 4 lots of a half is 2, and so that's minus 3, minus 1, 3. And then this row plus 8 of that one. 8 times minus a half is minus 4, so it's minus 2. 2 as well. That's plus 4. Okay. So what this says to me is that that the correct combination to produce 1, 0, 0. So to get 1, 0, 0, I need to go A is minus 2, B is minus 2, and C is 2. And so I need to do that combination of the inputs, which means the combination of the outputs will be minus 2 times whatever the original outputs were, minus 2 times the original outputs, plus 2 times the original output. Oh! Okay. And the original outputs were 3, 1, and -1, 5, and 8, 2. And so I get, fingers crossed I've done all this right. I get -6 plus 2 is -4. Plus 16 is wrong. Yep. Oh, crap ass. Yep. And up here, yeah, so something's, yeah, okay. So I should be subtracting 4 of these. So that should in fact be -1 plus 2, which is a 1. And this would be +1. And this would be 1 minus 2, which is -1. And so I've got that A is -2 and B is 1. A is -2 and B is 1 and C is -0.5. I totally messed that up, didn't I? Okay. I could still be wrong. As I said, the other one has slightly less scope for error, though there's minus signs going on. I would recommend it. But if you were not in an exam and had the ability to use a machine that could do row operations for you, the row operations might be quicker. If these vectors were just horrible numbers, then the row operations would be quicker. Yeah. Let's see, we've got -6 minus another 1, which is -7. And then -4 is -11. I think I've done the wrong. One of them had a -11 in the first spot, didn't it? No. Okay, I don't know. I'm just, that's okay. The world will make sense eventually. I've done something wrong. Something wrong somewhere. Sorry, guys. Yeah. Cool bananas. It should work. Yeah. Anyway. Yeah, there are multiple ways to do it. There is a different way to do it with row operations where you put your vectors in as rows instead of as columns. That's another way to do it. They definitely don't teach that one in this course. And there's another way to do it by using the fact that this really is an inverse here, and actually using the matrix inverse to do it. Yeah, so all of those things are possible. And at least one of the ones, the one with the inverse, comes back if you do any machine learning courses in the future. So, yeah. Right. Did we find an example of that other thing? No? Okay, well, we'll just leave it. Okay. Yeah. So this, just going back to what you said, what are the operations that are allowed? The plus and minus and multiplying by constants and dividing by constants, they're all allowed. And that is because that's the definition of what a linear transformation is, that you're allowed to do those things. That adding first is the same as adding after, and multiplying first is the same as multiplying after. And so those rules officially, even though it didn't look like I was using them explicitly, they were there. Every time I did any of these moves, I was using the laws of the linear transformations. Yeah. Whew, okay. I think that'll do. Thank you, everybody. And I'll stop the recording if I remember how to do that.